All right, ladies and gentlemen, I just wanted to give you a brief video on reading the periodic table. Understanding how to read the periodic table is important, and memorizing it really isn't what we should be focusing on, but rather understanding the parts of the periodic table and how to read it. So, looking at the periodic table, it is sorted in a series of rows and columns. Okay, the rows are called periods, and there are 7 periods in the periodic table. We have period 1, 2, 3, 4, 5, 6, and 7. Now these elements down here are part of the lanthanide and actinide series. They are separated from the table, but if you were to actually place them in their appropriate spot, they would start right about here and separate the table out and extend out. So, to give us a little bit of information on how this table works, each period that goes across talks a little bit about the shells of the individual atoms. We also have groups, and each group talks about how many electrons are in each shell. So I'm going to go into that a little bit more. First of all, let's look at the basic structure. Okay, we have 18 groups going across. Now, we're going to focus on the A groups today. If you notice on this periodic table, we have group 1, we're looking at the red, 1A, 2A, 3A, 4A, 5A, 6A, 7A. And in some periodic tables, it says 8A. In some periodic tables like this one, it says 0. Okay, but we're going to go with 8A. Okay, you'll notice the numbers in black go 1 through 18. That encompasses all of the groups. These elements here, this is the B group. These are actually the transition elements. We're not really going to talk about the transition elements because the purpose that we're looking behind separating the A group and B group won't apply for the transition elements. So looking at the A group, as we know, we have our elements sorted by atomic number. Okay, it does appear that the table is sorted by atomic mass, but that's actually not entirely true. There are certain instances, because of our average atomic mass and our isotopes, that our average atomic mass swaps between certain elements. Okay, it is actually apparent here between tellurium and iodine, where tellurium has a larger atomic mass than iodine. It's less than 1 atomic mass unit, but nonetheless, it is still larger. Okay, you can actually also see it between potassium and argon. Potassium has an atomic mass of 39.95. I'm sorry, argon has an atomic mass of 39.95, but potassium has an atomic mass of 39.10. Even though potassium appears after argon in the periodic table. But it is sorted by atomic number. Now, the atomic number is equal to the number of protons. Each element has its own unique atomic number. It equals the number of protons, and it is considered the identity of the element. So if you have an element, for example, that has 7 protons, that element is definitely nitrogen. There is no other element on the periodic table that would possess the same number of protons. So, looking at the periodic table, we are reading it from left to right, like we would read a page in a book. And the first period has hydrogen and helium. Okay? Hydrogen and helium are the only 2 elements in the first period. Hydrogen has 1 proton. Helium has 2 protons, but in a neutral atom, the number of protons and the number of electrons is the same. This is actually crucial to why elements are placed the way they are in the periodic table. So if you look at hydrogen, since hydrogen has 1 proton, it has 1 electron in its only shell. Helium has 2 electrons in its only shell, but since the first shell can only take 2 electrons, that shell for helium is completely full. That is why it is placed in this group. Okay, and we'll talk more about that in a moment. So when we look at period 2, now we have lithium through neon. Lithium through neon has, we are now working on our second period, so we're in our second shell, and lithium has 1 electron in its outer shell, beryllium has 2, 3, 4, 5, 6, 7, 8. Okay, so each atom has a maximum of 8 electrons in its outer shell. Okay, with the exception of one element on the periodic table, palladium, which gets rid of its last shell and gives that electron to the previous shell. It drops in energy level. It has 18 electrons in its outer shell. Every single element has between 1 and 8 electrons in its periodic, in its outer shell. So, if you look at hydrogen, hydrogen's placement is a little bit different than the rest of the placements on the periodic table. Okay, hydrogen does not fit the majority of the characteristics of the elements in the period or the group 1. Group 1 is known as the alkali metals. Because they're alkali metals, they all carry the same characteristics in that, they're metals. Hydrogen, however, is not a metal, but it is placed with group 1, although you can notice it is slightly apart, because it possesses characteristics of both group 1 and group 7. It may look like group 7, but it acts like group 1. So hydrogen moves to what is called the negative electrode. It forms a positive ion. In other words, it will lose its 1 electron and become positively charged. Okay? So when you do electrolysis, it will move to the negative electrode because positive and negatives attract, just like every other element in group 1. Okay? It also, because it forms positive ions, it moves to negative electrons. It behaves just like everything in group 1. But group 7, they tend to form diatomic molecules, and the majority of these are gases. Okay? And hydrogen is a gas, and it forms diatomic molecules. But its behavior primarily is the same as group 1, so it is more closely associated with group 1. So looking at what the groups are, group 1 are the alkali metals, group 2 are the alkaline earth metals. We already spoke about these being the transition metals. Okay, this is the boron group, the carbon group, the nitrogen group, and then we have the oxygen group. Now, the oxygen group is also sometimes known as the chalagens, okay? Group 7, these are the halogens, and group 8 are known as the noble gases. Now, group 8 is called the noble gas because those gases do not tend to interact naturally with any other elements. Although they've been forced to interact in a lab on occasion, they do not interact naturally with any other elements, and that is why they're called noble gases. Fun fact, our Constitution is sealed in a case full of helium, because since helium doesn't interact with anything, helium protects it from oxidizing and from deteriorating over time. Okay, so if you look at these groups, they are based on the number of electrons. So group 1 has 1 electron in its outer shell, group 2 has 2 electrons in the outer shell, group 3 has 3 electrons, group 4 has 4, 5 has 5, 6 has 6, 7 has 7, 8 has 8. Now notice I skipped over the transitions. Again, the transitions are a little wonky. They don't behave like the other ones. They tend to form different types of bonds, and some of them can form more than one type of bond depending on what it's bonding with. So we're gonna go ahead and we're gonna leave those alone. Okay, but when you're looking at groups 1A through 8A, those groups, the group number is equal to the number of electrons in the outer shell. The number of shells that they have is equal to the period that they're in. So period 1 has 1, shell, period 2 has 2, period 3 has 3, 4, 5, 6, and 7. And I don't know if you could see it, it's probably tiny on my periodic table, but these numbers here actually tell you how many electrons are in the outer shell. So, or in every shell, excuse me. So this, for example, iodine has 1, 2, 3, 4, 5 shells. So I have 1, 2, 3, 4, 5 sets of numbers. 2 in the first shell, 8 in the second shell, 18 in the third, 18 in the fourth, and its last shell or valence shell has 7. Okay? So, electrons generally tend to move around. They're either gained or lost, and that actually makes them makes certain elements very reactive. So for those of you who are familiar with video games, my classes have actually heard me use this analogy before. When you're playing a video game, there are very many games, quite often first-person shooters, that incorporate a status bar or an XP bar. And those of us who play them know that the higher you get up in XP levels, the harder it is to level up. So when you're at level 1, you can kill 1 or 2 things or do 1 or 2 tasks, and all of a sudden you've leveled up 2 levels. But then once you get to level 40, 50, 60, 70, or whatever the cap is in your game, it takes you a really long time to level up. So those of us that play games are very, very motivated when we're very close to the end of the status bar to level up, okay? But when we're in the middle of that status bar and we know it's not going to happen anytime soon, probably not even today or tomorrow, we might not be as motivated and may be able to walk away from the game. Well, let's kind of look at it in terms of the periodic table. Group 1 has 1 electron in its outer shell. It wants to reach that magical number of 8. Or in the case of hydrogen, it can only have 2. Now, hydrogen is prone to losing its electrons, so it actually gets rid of it and becomes a positively charged ion. But something like lithium will get rid of its 1 electron, and now the shell below it is completely full and stable and happy. Okay? Sodium will have a full shell of 8 if it gets rid of 1 electron in its outer shell. So it is very close to hitting that goal and getting rid of that 1 electron. And because it wants to do that, it is very, very reactive. So an element like sodium, for example, is actually explosive in the presence of water. Why? Because it wants to react. It wants to gain that stable outer shell. Okay? All atoms do. How close they are to doing that is an indication of how reactive they are. Okay, group 2 is also very reactive. Group 7 is highly reactive. Okay, once again, it only needs 1 more electron to finish its outer shell. So it is very, very motivated to get that 1 electron. So to give you an idea of how ionic bonds work, you have chlorine in group 7 and sodium in group 1. Sodium will give up that 1 electron. Chlorine will go ahead and take that electron and get its 8 electrons that it needs. Sodium is positively charged with a +1 charge. Chlorine is negatively charged with a -1 charge. And they get together and bond and form NaCl, what you commonly know as table salt. So, reactivity has to do with how close they are. The closer you get to the center, carbon, for example, it can go either way. They tend to be more sharing bonds, but for simplicity's sake, it would either take 4 or lose 4 because it has 4. So in that case, it's not going to be as reactive as something that's much, much closer to its goal. Group 8, they're not even at the party. They have a full outer shell. They are happy, they're content, and have no desire to take or lose electrons. So they are non-reactive. So I hope this helped give you a little bit of a picture on the periodic table. I know I talked a little bit about bonding as well, but one of the takeaways you should look at, the difference between a period, which goes across, and a group and what they represent. Our group numbers, particularly in the A group, represent how many electrons the outer shell possesses, and the period that an element is in will tell you how many electron shells or energy levels it has. I hope you found this of help. Please feel free to drop a comment if you have any questions or if you have something else you want me to address. And I hope you guys have a fabulous Thanksgiving. Take care.